What's going on, everybody? We have an absolute banger collab video for you all today. Special Relativity x Poset's collab. We're going to be talking a lot about some special relativity, some physics, and how that relates directly to the concept of partially ordered sets. We're going to start by taking a look at our claim and then get into some definitions. Claim: the set of causally related events in special relativity is a partial order, and an event A comes before an event B if and only if B is in the future light cone of A. A lot of words there that probably don't make a lot of sense to you if you've never seen special relativity in your physics classes before. So let's start with some definitions. The setting that we're going to look at for special relativity is called Minkowski space. And M is a four-dimensional space-time, and it can be represented with a metric tensor that has a signature plus, minus, minus, minus. What does that mean? Quite frankly, I don't really know. It has something to do with topology. The point is that there are four coordinates for each what is called an event. So an event is a point in Minkowski space-time that has a time, an x, a y, and a z position, right? From this, what we can draw is something that's called the space-time interval. Delta s quantity squared is equal to c, which is the speed of light, delta t squared, minus delta x squared, minus delta y squared, minus delta z squared. And right here, what we can see is our metric tensor signature. We have a positive term for our time coordinate and three negative terms for our spatial position coordinates. And what is special about this delta s squared is that we can effectively use it as a ruler. Delta s squared is going to measure the distance between points in Minkowski space-time in the same way that we can use, for example, the Pythagorean theorem to measure the distance between 2 points in normal Euclidean geometry. To this, we can add that two events, say A and B, can be considered causally connected if and only if this quantity is greater than or equal to 0. What does that kind of play into here? If we have a signal, for example, that was going faster than the speed of light, what we would see is that the distance that that signal travels in space is further than the distance that light would travel in that same time interval. And what would happen is that these negative terms would be greater than this, delta s squared would be negative, and that can't happen. If we have two signals or one signal between events that travels slower than the speed of light, then what we'll see is that the distance traveled here is less than how far light would travel in that same interval of time. This term would be greater than these, and delta s squared would be positive, or 0, right? Because all of those could be 0. But what this shows us is that two events can be causally connected if and only if delta s squared is greater than or equal to 0. From this, we can take a look at what is called the future light cone. If I make a coordinate axis, and we're going to put position on the horizontal, we'll say x, and time on the vertical, if I have an event A that happens right here at the origin, what can be affected by this event A? The other quirky thing we're going to do is we're going to scale our time axis by the speed of light. So this effectively non-dimensionalizes the system because both of these are in units of length. And the second thing that it helps us do is that now, if we have a signal that's moving at the speed of light, for example, a light beam, its slope in this system is 1. So this line with the slope of 1 is what forms the light cone. Now, anything that happens inside this cone, it's traveling less fast than this light beam. So anything inside this zone is possible. Anything outside of this zone would mean that a signal had to travel from A faster than the speed of light, which we know is not possible. So anything outside of this cone is not possible. It could not be causally connected to A. We could extend this axis into a second dimension, and we would have some cones that look something like this. We could try to draw a four-dimensional cone here. I don't know how to do that. But the point is that anything that happens within this cone is in the future light cone of A, and it could be causally connected to A. A signal could be sent here and received somewhere in here, and that is logical. This cone is what is described by this equation.
A few moments later.
Welcome back, everybody. We moved some pieces around, so now we can get to the proof. We want to show that this is a partial order. We need to show that it's reflexive, antisymmetric, and transitive. We're going to start with reflexivity. And we want to show that an event A is related to an event A under the partial order. Let's start with a picture. And we're just going to draw things in one space dimension, one time dimension. Here we have our x-axis and our CT axis. We put an event A here at the origin, and we can draw our light cone around A. We want to show that A is in its own light cone. We can see pretty clearly from the picture that A is in its own light cone. It's not outside of it, it's right there in its own light cone. Therefore, our relation is reflexive. We could look at our space-time interval, delta S squared, equals the time interval between A and itself is 0, and the position interval between A and itself is also 0. So our delta S squared is 0, which is less than or equal to 0. Therefore, A is in its own future light cone. Going on to our next piece, we want to show that our relation is anti-symmetric. If we start with our event A, what we want to do is draw an event B such that B is in A's future light cone and A is in B's future light cone. So if B is in A's future light cone, that would mean it's somewhere up here in this zone. But if B is also in A's future light cone, then the only place that we could possibly put B is at the exact same place as A. That's the only way they could both be within each other's future light cones. And if we have two events that happen at the exact same place in the exact same time, by the way that special relativity is defined in this context, they have to be the same event. Therefore, A and B are the same event, and A equals B. We can take a look at this mathematically as well and say that our delta S squared from A to B is equal to C delta T squared from A to B minus delta X squared from A to B, and our other position terms, which don't really matter that much here. And what we want is that this is less than or equal to 0 in both the A to B direction and the B to A direction. And since looking at these time and position intervals, when we're squaring them, the direction doesn't really matter all that much. So our direction from A to B also shouldn't really matter all that much. So the only way mathematically that this is possible is if delta T squared, or delta T, is 0, and delta X is also 0, and delta Y is 0, and delta Z is 0, which mathematically is showing us that these two events are at the exact same position, happen at the exact same time, therefore they are the same event. So, our relation is antisymmetric. The last piece we need to look at for our partial order proof is that our relation has to be transitive. If we start with an event A, and our second assumption is that B is in the future light cone of A, our first assumption, we can draw an event B. Let's just put it somewhere around here, sure. What we also know is that B is going to form its own future light cone because it's an event, which we can draw something like this. And what we observe is that the lines of this are parallel with the lines of this cone because it's the same speed of light between B and A. So if any event is going to happen here in B's light cone, for example, our event C, because of the geometry of the system and the way that B's light cone has to be drawn because the speed of light is invariant and a constant, C is going to be within A's light cone regardless of where B happens. Even if B was right here on the edge, B's light cone would look like this, and there's no possible way that C could happen outside of B's light cone. We could write this proof out mathematically using the exact same mathematical foundation with the space-time interval as we did with the others. We kind of have to bring in a little bit of extra math. You can look at this document that's linked hopefully in the description of this. But for right now, you can just take my word for it that this mathematically works out the same way as the other ones. And what we get is that our relation is transitive. If B is in A's future light cone and C is in B's future light cone, C is necessarily within A's future light cone. So we have shown that our relation for the set of causally related events, it is reflexive, it is antisymmetric, and it is transitive. Therefore, it is a partial order. I hope that made sense to you all. If anything didn't make sense, leave some questions in the comments. Look some of this stuff up, give it a Google. There's lots of information out there about special relativity and causally related events, light cones, diagrams, all things like that. But I hope this made sense to you. I hope you learned something, and I hope you all have an awesome day.